Asymmetric encryption relies on a mathematically linked pair of keys, a public key for encryption and a private key for decryption. This dual key structure ensures that data remains secure even when the public key is shared openly.
The public key is designed for widespread distribution, allowing anyone to encrypt data intended for you. Conversely, the private key must remain strictly confidential, as it is the only mechanism capable of decrypting that information or signing digital messages to prove identity. To establish trust, an entity generates a certificate signing request, or CSR. This file contains the entity's public key and identity information, serving as a formal application to a certificate authority for validation. The certificate authority validates the request and issues an X.509 digital certificate. This certificate acts as a digital passport, cryptographically binding an identity to a public key and providing a verifiable proof of authenticity. These components converge during a TLS handshake, where the server presents its certificate to the client. Through this exchange, both parties verify identities and negotiate secure keys, creating an encrypted tunnel for private communication. We begin by clearing the terminal and generating a new RSA private key. Using openssl, we create a 2048-bit key saved as key.pem. This file acts as the foundation for our cryptographic identity, so keep it secure. Next, we verify the integrity of the generated key file. The -check flag ensures the key is properly formatted and mathematically sound. Seeing the output confirms that our private key is ready for use in subsequent signing operations. Now we generate a certificate signing request, or CSR, using our private key. We specify a common name of test within the subject field. This request contains the public information that will eventually be included in our digital certificate. This ensures our request is pre-configured and ready for the signing process. We inspect the contents of the newly created CSR file. By using the text and noout flags, we display the human-readable details of the request. This allows us to confirm that the subject information and public key data are correctly encoded. With the CSR ready, we self-sign it to produce a digital certificate. We set the validity period to 365 days using the -days flag. This creates a cert.pem file, effectively acting as our own certificate authority. Finally, we examine the generated certificate to verify its details. The output shows the issuer, subject, and validity dates, confirming the certificate is properly signed and structured. We have successfully completed the full cycle of key generation and self-signed certification. Notice the signature value at the bottom, which uses the SHA-256 with RSA encryption algorithm. This cryptographic hash ensures the integrity of your certificate, proving it hasn't been tampered with. By verifying these hex-encoded blocks, you confirm that your private key successfully signed the public identity information.